Okay, so let's start today's lecture. So we'll talk about some constructs in answer set programming. So the two things that we'll talk today is choice rules and constraints. And they're actually more than this, but after studying this, I hope you can get some idea about ASP programming methodology. So we'll see some examples of the actual programming. Okay. Okay, so what are these choice rules? So this is denoted as the curly brace, the set brace, and the atoms are separated by semicolon. Okay, so one of the homework problem, also in the assessment, was about the choice rules, and I hinted last time what this choice rule is about. So if you have something like P with choice, that is just a shorthand notation for P or not P. So what are the stable models of this choice rule, P or not P? Empty set and singleton set P, right? So according to this choice rule P. And the name choice comes from this fact that it allows us to choose to include P or not, okay? And if you can actually have more than one. So here you see two atoms, PA and QB, are inside the set brace. And that is basically P of A or not PA, conjunction with Q of B or not Q of B. Okay? So that's the conjunction of two choice rules. Now, then what are the stable models of this formula? Empty set, singleton set PA. So let's say what are the stable models? Okay, in this case we have empty set, P of A, Q of B, and P of A, QB. If you're in doubt, of course you can check the reduct relative to each of these set and check whether each set is a minimal model of the reduct. Okay, so by now you should be able to do that by yourself. So here I will just say that there are four stable models here. Now each of the stable model is a subset of PA, QB. Right, so there are four subsets of this this set PA, QB. Okay. Right. So what this tells us is we can use these choice rules to generate some possible choices from the beginning. Okay. So you can run the program with this command. So clingo. Followed by the name of the file. So it's one line program, I call it choice.lp, and put 0 at the end. So it will return all stable models. And here denoted by answer in terms of clingo output. So there are four answers, okay, or four stable models. The first one is empty, which just basically means empty set. Okay? All right? Any question up to this part? Okay, so we'll do a lot of exercise on this thing. Okay, now you can simplify the choice rules in some cases. For instance, if you have choice from number 1 to 100, you don't want to say 1 semicolon, P of 1 semicolon, P of 2 semicolon, P of 3 semicolon, and so on and so forth. Okay, so instead of that, you can write interval notation. So if you say P1 dot 3, then this is actually same as generating the atoms inside P1, P2, P3, and as the choice for this. Okay, so how many stable models are here for this one line? 8. There are 8 because there are 3 atoms to choose. So 2 times 2 times 2, or 2 to the power of 3. Okay, good. Now, if you have a symbolic constant, not the number, you cannot actually use the interval notation because interval notation is valid for the integers. But you can write this pooling, which you can put the argument of the predicate together. So this is not really much of saving, but it helps you to write something more neatly or something more concisely. So if you have A, B, C to be included in P, you can write this one predicate followed by this A semicolon B semicolon C. Okay. All right. So then here's an exercise for you. Maybe let's do the piece. Okay. All right. So let's open the Socrative. Let me just first open it. Okay, so this one, P1.3, Q1.3. So how many stable models will be there? Let's do the second one as well. Okay, so just write two numbers. Okay, so how many stable models are there for the first one? How many stable models are there for the second one? Are you done? Okay, let's see. Okay, some people didn't submit answers yet. Okay, so let's see what you answered here. Okay. So 64, 5, 12, 64, 36, 64, 8. Okay, so many people say 64, 63, or 16. Okay, so the first one seems to be that 64 is the dominant answer. The second one is a bit more diverse. Okay, what is the majority? I do see some 512 to 2009, but also 16, 8, 32. Okay, so there's a varying answers here. Okay. So let's do this together. So the first thing here we have P1.3 and another one is Q1.3, right? So how many stable models were there for the P1.3 in the previous slide? 8. And how many are in the, of course, in the Q1.3? There should be also 8, right? And this is a conjunction. So you have a combination. So what this should be the answer? 64 is the right answer. Good. What about the second one? The second one has this interval, right? Now, how many atoms will be generated inside this set? 9, because it's a P1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. So there are 9 atoms that will be generated. And each of the 9 atoms can be either chosen or not. So that's the 2 to the power 9, which is 512. Okay? Yes?
For the first one, should we count the empty set twice?
Empty set cannot be counted twice. Yes, that's a good question. Empty set cannot be counted. So does it matter? No, we don't count the empty set twice. Does it matter? I don't think so, right? So you have still, no. I don't think it actually matters, right? So empty set, and this basically you have 6 atoms to choose, so 2 to the power 6, right? Because you cannot really, when you cross product, you cannot have the empty set counted twice. We are not adding, we are multiplying. Okay? If you're in doubt, you can try. Okay? So all this code can be actually run in Klingo. Okay? And that's actually what your homework 3 is about, running Klingo to verify each of these claims. Okay? All right, so let's go to some more extensions. Now you can put some bound in this set. Okay, so basically this set gives us some choice. You can actually put the lower bound and upper bound to say the cardinality of the set was that I choose should be containing at least 1 atom and at most 2 atoms. Okay, so here you can try to find the subset of 1, 2, 3 that consists of 1 or 2 elements. Okay, in other words, the set whose cardinality is either 1 or 2. How many stable models are here then? How many subsets of the P1, P2, P3 satisfies the cardinality constraint that the cardinality is either 1 or 2?
6.
There are 6. Only 2 extreme cases are eliminated. Empty set, cardinality is 0, and P1, P2, P3, cardinality 3. So those 2 sets are eliminated, and all the other remaining things becomes a stable model. Okay, so here you can be a bit more tuning in the fine-grained level. Not only the arbitrary choice of this set, but you can choose the bound. Okay, and this actually helps often in some programming. Okay, so here is then the question for you. Okay, how many stable models will be there for the first one? 63 now. Why? Because empty set is the only one that violates this cardinality bound, right? So the set should contain at least 1 element. Right? Only the empty set is the one that is a subset of P1 to P6 that does not satisfy the lower bound cardinality, right? Okay, so there are 63. How many stable models will be there for this one-line program? So you have to choose among the 6 atoms, P1, P2, up to P6, whose cardinality is exactly 3. Okay? So that's 6 choose 3, right? What is the number?
20.
20. Okay? So there are 20 and there are 63. Okay? All right. That's good. The next one. Here we're trying to find a simpler rule than this one. So if you have lower bound 0, how can you simplify this rule? Huh? you actually don't need this thing, right? So 0 as a low bound doesn't give any further information. So the simpler one is simply just P of A. Good. What about this guy? How can you simplify this?
Just like
So this one says you choose the subset of PA. There are only two subsets, empty set and P of A, but the cardinality should be 1, which means this is actually just same way to say P of A. P of A must be true. Okay? So it seems like you're giving the choice and then you bound it. It turns out that there is only one case that satisfies this. So you can just write P of A as a program, and the answer set will be only P of A, the singleton set P of A. Okay? Good. What about this guy?
empty set.
Somebody says empty set. Is it the case? I don't think so. Okay. So P of A with upper bound 1. Again, like A, it does not give much more information, right? You can choose only up to one atom from the set P of A. So this is actually redundant. So this is actually same as P of A. Okay? So in each of the case, this one, if you give it as an input to Klingo, versus this one giving as an input to Klingo, they produce the same stable models. Okay? All right, the next one. Now we start to use variables. Okay? So I don't want to write too lengthy code. Sometimes things are repeated. I can use actually variables, and this is actually handy for most of the cases. Now, if you use variables like this, so Klingo first tried to eliminate these variables to produce positional image. That's what we studied in the previous handout. If you have P of X and Q of X, and X is 1 to 2, this is basically same as replace X with all possible occurrences. Okay? Now, the definition of proportional image, if you strictly follow, X will be replaced by any numbers and any symbolic constants. But not all of them are actually meaningful. Okay? Because some of them will result in, actually many of them will result in false in the body. Right? So this rule, if you make a proportional image, it will actually produce two rules, where X is replaced by 1. Now another one is when X is replaced by 2. Now there are also other rules in the proportional image, but when X is not replaced by either 1 or 2, that will result in bottom. And those rules are actually redundant. So we can forget about those kind of additional rules. So let's just look at these core rules, these two important rules. Okay? So then, now you know, after you turn into this propositional program, you can find out what are the stable models. Okay? So this is actually reducing to the ones in the previous slide. Right? How many stable models are here? 4. Why? Why? Somebody can raise hand. Arindam?
Yes, so the first choice we can give either P1 or Q1, and we can multiply that with either P2 or Q2.
Yeah. So the first one says choose 1 from P1 and Q1. And the second one is choose 1 from P2, Q2. Right? So you can choose either P1 and P2, or P1 and Q2, or Q1 and P2, and Q1 and Q2. So there are 4 possible combinations which are shown here. Empty set is not possible because now the upper bound and lower bound is 1 and 1. So you have to choose exactly 1 from each of this set. Okay? All right, good. Life is full of choice, right? Okay, one thing that I hit here is X is so-called global variable. Okay, so this is called global variable. I didn't actually say what is a local variable. And I'm going to talk about this more in the next slide, but let's say in the global variable, what happens is when you replace the variable with some specific instances, the number of rules will increase. Okay, so here x ranges over 1 and 2 values. So when this rule is grounded, it will generate two ground rules, two essential ground rules. Ground means that there is no variable. Okay. Sometimes we actually use so-called local variable, and using this combination carefully is one of the success of answer set programming. So here is one pedagogical example. So here an index is a predicate that contains 1 to 7. So in other words, if you look at the first line, any stable model must contain index of 1, index of 2, up to index of 7, right? Now, the next one is a program that contains local variable. Okay, so I don't know whether you're keen to see the difference between this occurrence of I and the previous occurrence of X. Okay, I'm going to explain that, but here I is so-called local variable. Okay, and note the difference that the I actually occurs only inside these curly braces. It does not have occurrence in the outside. So those variables are called local variables. So you can say, what is a local variable? It's a variable such that all its occurrences are limited inside this scope of curly brace. Okay, so that's a local variable. Okay, because there are only 2 occurrences of I, and they are all bounded by this curly brace. Okay, so this is called local variable. Now what are the global variables? Global variables are all other variables that are not local. Okay. Okay, so what happens to the instantiation of the local variable? If you remember the intentional notation for the set, okay, so you know the difference between intentional and extensional representation of set. In the extensional representation, you enumerate all elements in the set. In the intentional notation, you write the conditions for being in a set. Okay, so this is actually, you can read it as intentional notation. So here, if Q is true, the second rule says if Q is true, then this set, you select element from this set, where this set contains P of I, such that index of I is true. Okay? So what that means is basically Klingo will understand the second rule in terms of the rule that I've shown here. Okay? So it will instantiate the variable I. But unlike in the previous example, this instantiation will make the set to be large. I mean, the set instantiation is within the scope of this set. Okay. So instead of generating more rules, it will not generate more rules. It is still only one rule, but the inside will be fully instantiated, depending on this condition that you are given. So index I can go from 1 to 7. So here, this P of I can go from 1 to 7. Okay? So if you see this rule, you can view this as an abbreviation of this rule. And obviously, if you increase the size of the index 1 to 1000, all you need to do is to change this one to be 1000. Okay? Then Klingo will populate this one going from P1 to P1000. So you don't have to type 1,000 atoms by yourself. Okay? Are we together? Let's contrast this with global variable. So here is a similar example, but using the global variable. And here, I is a global variable. Why? Because it has an occurrence outside the curly brace. So there are actually two occurrences of I, and one of these occurrences, the second occurrence of I, is outside the curly brace. So I is called a global variable. Okay? So for the global variable, the rule is actually simpler. Basically, as I told you before, it will just generate multiple rules where each rule will replace the occurrence of I with the instance of I. Okay? So here, this one denotes 7 rules because I can go from, index can go from 1 to 7. So I ranges over 1 to 7. Okay? Any question up to this part? Yes?
In the previous slide, does the comma denote a conjunction or a disjunction, or it doesn't matter?
Oh, you're right. Actually, this is a typo. This should be semicolon. Yeah, thank you. The reason for that is the previous version of Klingo actually used comma for the separator inside set, but the new version actually used semicolon. So. So semicolon is actually the new delimiter for this case, yes. All right, so, okay, so we are done with the choice rules, and we'll now look at another construct, and this is called constraint. What is a constraint? This is a simple rule that has empty head, okay? Or we actually talk about this when this is empty head, we will understand as bottom. So this is false if P1. Okay? So what are these rules doing? So basically when you add this constraint, what will happen is you will weed out some stable models that violate this constraint. So the constraint is saying that P of 1 must be false. Okay, that's what the constraint is saying. Okay, let's do a simpler example first. So I can write P over Q. Now I can write this P. What are the stable models of this program? P. So the stable model here is P. True? Let's check this. So if this is P, okay, we form the reduct, right? Okay, what is the reduct of this program relative to P? Same, because there is no critical path. There is no negation. We have to check whether P is a minimal model of this program. Is it? It's not even empty set. Don't go into empty set yet. Is P a model of this reduct? No. Why is not a model? Because of the constraint that I just added. This is P implies false, which is same as negation of P. Right? So when I add this constraint, what will happen is whatever that has P inside cannot be a stable model anymore. You can weed out those stable models that violate this constraint. So what should be the right stable model in this case? Q only, right? Note here that the original program P over Q, okay, the first rule, has two stable models, singleton set P and singleton set Q. But when you add this constraint, you're eliminating one of them, which contains the P, right? Do you see some similarity between this one and something that we discussed earlier? What is that? When you add more formulas, you always decrease number of models. What is it called? What is that property called? That's called monotonicity. Okay? So monotonicity means if you add more formulas, the set of models will decrease. The set of models that does not satisfy the additional formulas that are being added, they will be no longer the model of the expanded program, right? That's called monotonicity. Now, we talked about this before. The stable model semantics is non-monotonic. It does not behave that way. However, you can actually simulate this behavior using this constraint. When you add constraint, you always eliminate stable models that violate the constraint. I don't know whether you're following here, okay? Let's actually play with some other example. How many stable models are here? Two. Okay? So they're empty set and P. I'm now going to add a constraint P. What will happen to this stable model? So now I consider these two rule program. What are the stable models? Empty set. Okay, because this guy, so between these two, only this will be remaining as a stable model, but this guy will not. Okay? Because it violates this. So you can actually look at the stable models of the original program, and then you can you can remove some stable models that do not satisfy the constraints that are being added. Okay? Let's try something else. What are the stable models for, actually let's write here. In this case, empty set does not satisfy the additional constraint that we just had. So it's only the empty set. Oh, P, I'm sorry. Singleton said P. So that's the stable models of this, because this P satisfies this. Okay? All right, so let's do some exercises here. So basically what I say here is, if you add this one, okay, or if you see the program that contains this constraint, then you can actually reason about the stable models in a compositional way. You can just look at this part first and find out what are the stable models. Okay? Sometimes that's easier to do. Okay? Rather than just looking at the whole program. Okay? Just look at some part of the program that does not contain this constraint, and then get these stable models for this program, and check whether each of them satisfy the additional constraint. Okay? If it violates the constraint, throw that away, and all the remaining stable models will be the stable models of the whole program. Okay? So we'll do this exercise now. So for the first program, the leftmost one, how many stable models are there?
5.
How many?
4. 7.
Okay, so how do we reason? Just look at the first one. How many stable models are there for the first rule?
8.
There are 8. How many of them contains does not contain P1?
4.
Maybe I should have asked differently. How many of them contains P of 1? 4. That's the same the other way, right? So those 4 will be removed because they violate this constraint, right? The constraint is saying don't include P of 1. Okay, those subsets of P1, P2, P3 that contains P1, they will violate this constraint if they contain P of 1, right? So only 4 of them do not contain P of 1, and they will be the stable model here. Are we together? Okay. Let's give a quiz then. I'll ask you to do these 2, okay? Let me just change this. So this time, you can talk with your neighbor, and if your neighbor give you more convincing answer, you can write his answer or her answer. Okay. So, yeah, you see, just say how many stable models are here and how many stable models are here. All right, so let's see what we got. Oh, only 15 answers. Okay, so let's hide. Okay, finish up. Okay, so let's see. 6 2 6 2 2 2 6 6 2 5 2 2. Okay, so they are more or less in the range. It's not like 100 or whatever, right? So I guess you guys are following the materials. So what is the right answer? 6 6. Looks like that's also the majority here, although it's not clear enough. Okay, let's check it. So the second rule is saying that you have to generate all subsets of P1, P2, P3, but you have to read out those stable models that contains P1 and P2 together. How many subsets of P1, P2, P3 contains both P1 and P2 together? 2, which are P1, P2, and the total set, yeah, P1, P2, P3. So 8 minus 2 is 6. So there are only 6 stable models here. What about this guy? So this guy is saying that you have to choose now the subset, but if it is not containing P1 and not containing P2, then it violates the constraint. So it's a kind of doubly negated. So sometimes it helps you if you write this in terms of the logical formula and simplify it. So this one is same as not P1 and not P2, and this implies bottom, right? Which is basically same as negation of not P1. Okay, let me write again. Negation of not P1 and not P2, which is again equivalent to P1 or P2. So basically it is asking how many stable models how many subsets of P1, P2, P3 contains both either P1 or P2 or maybe both, right? So how many of them actually do not contain neither P1 and P2? There are 2 answer sets, those 2 stable models, like empty set and singleton test set P3. They're the only 2 that do not contain neither of these P1 and P2. So if you get rid of those 2, then the remaining 6 will be the stable models of the whole program. So there are different stable models, but the number of them are the same. And we don't have time for doing that, but this is actually interesting. You will actually realize what happens here is, in the same way, this is negation of P1 and not P2, which is same as not P1 or P2, which is basically same as P1 implies P2. So here is a way to kind of simulate the implication, okay, in the body. So any stable model, if P1 is contained, P2 must be contained in the stable models. That's what the constraint is saying. Okay? All right. Okay, so the next thing is now, as you see, there's something, some relation between the cardinality bound that you saw before versus the constraint, right? So obviously here we start with these things, generate arbitrary choice, and then we eliminate some of them. You could have gone this some different way. You can actually give a bound for each of them. So they are not necessarily identical, but sometimes you can write the one method in terms of another method. So here, for instance, if you have this rule, P of A and QB. So basically choose the subset of this PA and QB, but at most one element. So cardinality is bound by one. So that is actually the same as just choose any subset, but do not choose the one that contains both P of A and Q of B. So here you use the cardinality bound to represent the stable models, and that can be replaced sometimes with this choice rule plus choice rule without the cardinality bound, but with using this constraint. Okay? Okay, and you can do the similar transformation with this guy, and I'll leave this as an exercise. Okay, so here the upper bound can be replaced by this guy. Okay, and here the lower bound can be also eliminated if you use constraint. And the hint is actually the one that we just saw in the previous slide. Okay, all right. So we don't we don't go into the proof of this theorem, but what you can see is propositional logic can be actually embedded into the stable model semantics. So although Klingo is an answer set solver, it can actually find the models of propositional logic. So it can work as a set solver, satisfiability solver. The way that you do is basically coming from this choice rule. Okay, so what is the model in the propositional logic? The models are the ones that satisfy the given formula F, right? Now, how do we simulate this idea in stable models? So what you can do is you write the same program. Okay, I'm sorry. You actually generate all possible choices. You generate all possible interpretations and eliminate those interpretations that do not satisfy these rules, the given formula. Okay, so maybe I should explain with this example. So F equals P or Q. How many models are here? What? Models. Okay, we are going back to the basic, right? There are three models. So models means assuming that, of course, PQ are only the signature. So models is empty set, P, and Q. Now, if you ask to find the stable models, what are the stable models? Actually, why do I have this empty? It's actually PQ, right? Okay. So what are the stable models of P or Q? Only the first two, right? Because in this case, stable models are the minimal models. So it looks like it's difficult to represent the concept of models in terms of stable models. But what we can do is taking this and transform into another program such that its stable models will be the stable models. So what we want to design is this. Stable models of this translation are exactly the models of the original program. So this is what we want to get. If you are familiar with the theoretical computer science, there's a reduction idea. So if you want to solve one problem, sometimes you can reduce that problem A into problem B, and using this algorithm or solver for B, which will also solve the problem A. Okay, so we are working on that. So what is actually this transformation? It's actually simple now once you use the choice rules. Basically, you write P, Q, okay? And then write P or Q. Okay, let's consider this. Okay. So reason this the same way. What are the stable models of the first line? Yeah, there are 4, right? All the subsets of PQ. Now, if I add this constraint, what will be the remaining stable models? Well, let's say this way. If I add this one, among the 4 stable models of this guy, which one violate this constraint? Empty set, right? Empty set makes this false or false, then this becomes true. True implies false is false. Only the empty set violate this, which means that there are remaining 3, which is simple, these singleton sets and PQ are stable models of this guy. Now, if you look at this guy, these are exactly the models of the original formula. Okay? So, I can understand the models of the original formula in terms of stable models of the translation. And they are in one-to-one correspondence. Actually, they're exactly the same. Okay? Which means you can use Klingo to find the models of propositional formula. Okay? Any question up to this part? Okay, good. So now you mastered answer set programming, or at least the basic construct of answer set programming. So let's go down the mountain and let's face the competition. Okay, this is what usually the kung fu movie is doing. So when somebody whose father or parents were killed by the enemy, they go to Shaolin Temple and train with martial art and then come back and defeat. Okay? So we are now in the phase of coming back to the mountain. So you had hard training on the stable models. So let's try to use it. What sense that we are doing this? Here I'm going to use one way to organize rules in answer set programming. This is a 3-part. There are 3 parts. Actually, we are going to use 2 parts, the first and the third part for the most of the time. And you already encountered this when we do the choice rule and the constraint. So the first part of the program is to generate solution space from the upper bound. Okay, so you want to solve some problem, and the problems may have multiple solutions. Okay, let's try to generate all possible solutions. Okay, now some of the possible solutions that you generated as candidate may not necessarily be the solution for the original problem. Then get rid of those things. Okay. So let's illustrate this idea with this n-queens problem, which we have seen before. Now, you remember when n equals 3, there is no solution for this problem. When n equals 4, there are actually 2 solutions. N equals 5, 10 solutions. 6, actually surprisingly, the number goes down, so there are only 4 solutions. But from then on, actually increases. Okay? And you can actually generate all possible solutions very quickly. So how do we do that? Now let's revisit the program that you have seen before. Now you can really understand how to write this program. Okay, so what are the conditions that we have to represent? When we do the answer set programming, the representation, we are representing the specification of the problem in terms of answer set programs, the programs that has stable models, right? So you have to try to think about the English statement as a formal representation first, right? So try to be as formal as possible. So turn the English into some more structured way. So if you look at this problem, there are these constraints. Each column should have exactly 1 queen. Each row has exactly 1 queen, and each diagonal has exactly 1 queen, right? That's what we have to say. So how do we say each column has exactly 1 queen? So this is the rule that uses both local variable and global variable. Okay? So my question is, what is a local variable here? And what is, actually, we have actually j as the only variable. Okay? So is j a local variable or global variable? It's global. Why? Okay, so you guys are good. Just 30 minutes ago we talked about this. You still remember it. Amazing. So j is a global variable because it has an occurrence outside this curly brace. And what we do is just to enumerate the rules, right? So generate each rule where n is the j is replaced by this number. So now this n is actually placeholder. You can actually change the parameter n when you're giving the command line. So let's say, for simplicity for now, let's say n equals 3. Okay? Now if I call Klingo, how many ground rules that Klingo will generate from this rule? 3. 3, because j goes 1 to 3. So one of the rule is 1 q 1 dot dot 3 1 okay. Am I missing? I'm missing. Okay, I should have. Okay, let me rewrite again. Okay, let me actually delete this guy. Okay. So basically, you generate these 3 rules. Good. Now, after that, we see the interval inside, right? So how does the interval work? How many atoms will be here? 3. So this rule, for instance, the first one will have okay? So we are doing the propositionalization, and the next rule will be similar, but now j is 2, right? Similarly, good. Okay, now the question. How many stable models will be here? So look at those propositional program. How many stable models are generated from this rule? So in order to answer that, I turned into this way. First, eliminate all global variable, and then do the instantiation inside the set using this interval. So this is the program that you can look at. Okay, how many stable models are generated from this? 27, because now you know this is 1 and 1. You have to choose exactly 1 from the first set, 1 from the second set, 1 from the third set. Each set has 3 choices. So this is 3 times 3 times 3. That's 27. There are 27 stable models. Okay? Now obviously this one only says if you have this one, each so let's say 1, 1, 2, 1, 3, 1. If you think, if you look at this, this means among these 3 positions, you have to choose 1 position to put the queen. The second rule is saying among these 3 positions, you have to choose 1. The next one, among maybe this 3 positions, you have to choose 1. Okay? So for each column, we are selecting exactly 1 position and put the queen there. Now, for the same column, there is only exactly 1. But if you just have this one, it might be the case that the same row has multiple queens, right? Okay, how can we eliminate that? So the next one is, I don't want the stable models to encode that the same queens, 2 or more queens are on the same row. And I can easily write this way. So if I have Q I comma j and I comma j1, and j1 are different, okay, then this violates the constraint. In other words, here I is the same variable, right? So for instance, one of the instantiation will say q of 1 comma 2 and q of 1 comma 3 if I is 1 and j equals 2 and j1 equals 3, right? So one of the instantiation will give this one, which means you cannot have 2 pins in 1 comma 2 and 1 comma 3. Okay? Now obviously this is one of the only instance of these rules. So here I, j, j1 ranges over 1 to 3. So there are actually many ground rules in this case. And together, together, they eliminate all stable models that has say, 2 pins on the same row. Okay? Yes.
So we didn't write j not equal to j1 because it will produce less number of propositions.
Can you say again?
So here we wanted to say that no 2 pins are on the same row, but we used j less than j1.
Oh, yeah.
Not equal.
Yeah, it actually does not matter. Yeah, that's a good question. You can use actually j not equal to j1. In this case, you will have all the combination 1, 2, 2, 1, 1, 3, 3, 1, right? But actually that's not really essential because having this one versus this one, okay, it actually means the same. So the order of this does not matter. So if you write this way, you will actually generate half of these instances, and that may help. Okay. So it does not really matter which one that you use. Are we done? So we until now we have placed the queens so that they are on the same column. I mean, no 2 queens are on the same column, no 2 queens are on the same row. But what about the diagonal? So we have to get rid of that. So how do we represent? So similar to the second one, if we have 2 positions I comma j and I1 comma j1, and if j is different from j1, which means that these 2 are the distinct positions. Okay, you can write in a slightly different way, but that does not matter. But the interesting thing is when you have the absolute value difference, okay? So I1 minus I and J1 minus J are equal. That means they are on the same diagonal. Okay? So then this violates the constraint. So if you add these 2 constraints together with the first choice rules, then you are done. Okay? All right. So let's see if we can see this. So this is the program. Okay, that is exactly the same program I copied. Okay. So let's check Klingo 5. When n equals 3, how many solutions are there? No solution. So Klingo say no. There is no solution. If it is 4, okay, actually I should put 0 at the end. So there are 2 solutions. Okay. If it is 5, there are 10. If it is 6, 4. Okay. If it is 7, 40. If it is 8, 92. If it is 9, 350. If it is 10, 724. You got the idea, right? Okay, so it's actually easy to write the program, and all hard work is done by the answers solver, Klingo, right? You don't have to worry about those algorithms and how to enumerate, right? Okay, that's good. Okay, so this is what you do. I don't have to repeat this. You can just look it up. Okay, so let's actually do another problem. So there's something called Short number, which is defined in terms of some free sets. So we say a set of integers is sum free if there are no numbers x, y in A such that their addition is also in the same set. Okay? So for instance, if you have 1, 3, 5, is it sum free? Because when you add two numbers, 1 plus 3, 4, 4 is not there. 3 plus 5, 8, 8 is not there. 5 plus 1, 4, 4 is not there. 5 plus 1 is 6, 6 is not there. Okay? So their addition is not in the same set. What about this? Is this sum free? Actually, I should say that this x and y do not need to be distinct from each other. So 1, 2 is not sum free because 1 plus 1 equals 2. So you just pick any two numbers which may be duplicate. If their sum is not in the same set, you say this is sum free set. Now, what is a short number? Short number sk is the largest integer such that the interval 1 through n can be partitioned into k sum free sets. Well, this is actually a long definition. So let's actually try to understand. So it's a good idea to view this k as like a bucket. So you are given k bucket, and you have to place a number 1 through n, so that each bucket is sum free. Okay. So let's play with this idea. In fact, actually, sk should be actually the largest interval because smaller interval is actually easy to partition into sum free sets. So we want to understand maybe S of 1. So what is S of 1? In S of 1, you are given only one bucket. Okay, and you have to place some number from 1 to n. Larger the better. If you have a larger n, that's the best. Okay, that's the short number. Okay. What is the biggest interval, 1 through n, so that you can place in one bucket so that this bucket is sum free? So if you don't know any method, you can just try very naively. So starting with interval 1, 1, interval 1, right? Can you put 1 into the one bucket so that this bucket is sum free? Yes, right? If you just put 1, 1 plus 1 is 2. 2 is not in the same bucket. Okay? Your goal is to make each bucket to be sum free. On the other hand, you are given the interval. You are not choosing any random numbers. You are giving a number from 1 to n. Okay? And we want to find the largest n that we can divide into k sum free sets. So 1 is possible, which means that S of 1 is at least 1. What about 1, 2? Can you put 1 and 2 into one bucket so that this bucket is sum free? No. No. Okay? So then what is S of 1? It's actually 1.
What
okay?
All the odd numbers you can
The number should start from 1 to n.
Okay.
Okay, that's actually what is given. This interval 1 to n. You are not choosing random numbers. Okay? Alright. So let's do this one. Now you have two buckets. Okay? So obviously you can put 1, that's fine. 1, 2. Can you put 1 and 2 into two buckets? You don't have to use all buckets, by the way. Okay? But can you make each of the set sum free? How do you do that?
one bucket will contain
1 and
other will contain
2. You cannot put 2 here because 1 plus 1 equals 2. Okay? Okay, but you can put 2 here. 2 plus 2 equals 4. 4 is not in the seconds bucket. Okay, and everybody is happy. What about 1, 2, 3? Okay, let me erase this one. Okay, I have now 1, 2, 3 bucket. And can I put 1, 2, 3?
Yes.
Yeah, okay, so that's no problem. What is the larger number than 3? If I have, say, 1, 2, 3, 4, can I put it into, actually, why do I have 3? Sorry. Yes, I have to get rid of this. We are talking about S of 2, so 2 bucket. Okay? Good. All right, so 1, 2, 3, 4. Can I put into 2 bucket?
Yes.
Yeah, how do we do?
1, 4.
So here's a naive idea. So let's try 1, and we know that this 2. Okay, I can choose 3 to be here. Okay, then I cannot put 4 here, so I have to put 4 here. And then what happens? This is not sum free. Why? Because 2 plus 2 equals 4. So what did I do wrong? I should not have put 3 here, but if I have put 3 here, then I could put 4 here, and then everybody is happy. So I had a choice, and this choice point is what makes this short number very complicated mathematical object. Okay? So 4 is the right answer, but in order to get into 4, you should have put the 3 into the right bucket. Okay? And it turns out that this is all you can do. So this is 4. If I have time, we can do that. Okay. Let's do this. S of 3. So now we have 3 bucket. Okay? And this time, anyone who has the number, you can try. So we have 3 buckets. What is the largest n, 1 to n, that we can put into the 3 sum free sets? 9? 11? Okay. 11 beats 9, because if 11 is a correct answer, then we don't have to look into 9, because in the shared number we have to look at the largest interval. Okay? As you know, if larger and larger, it becomes more and more difficult to make these sets sum free, right? So currently 11 is the winner, right? Okay. Any other answer as we go? 9? 9 is okay. 11. So can you tell me what should we put here?
1, 4, 6, 8 for the first part.
1, 4, 6, 8, and then
Second is 2, 5, 10, 11.
2, 5, 10, 11.
Third is 3, 7, 9.
3, 7, 9. Okay, so let's see. Are we fine? Looks like we have a problem. What is the problem here? 5 and 10 should not be put into together, because 5 plus 5 equals 10, so this is not good. So 11 was defeated. Okay, what about 9? Somebody said 9. Just speed out here. What? 1, 4, 2, 3.
No, 1,
1, 4, and then the next one is 2, 3.
and then 5, 6.
5, 6.
5, 6, 7, 8, 9.
7, 8, 9. This is the one. Okay. So let's see. Are we fine? It looks like I don't see a counter example. So if somebody else doesn't say anything negative, then this seems to indicate S of 3 is at least 9. Can you make it 10?
Yes.
Can you make it 11?
Yes.
Can you make 12?
Yes.
Can you make 13? Can you make 14? Okay, the answer is actually 13. If you have sneaked into the next slide, that is the answer. Since we don't have much time, if you are interested, you can try by yourself. I want to just tell you some interesting history. So I taught this material last year, and until then, S of 4 was known. S of 4 bucket, you can only make 1 to 44 to be divided into 4 sum free sets. And then from S of 5, nobody knew the answer. There was an old paper that says S of 5 should be between 160 to 315. That was in 1979. And S of 5 was actually shown to be exactly 160 in last year, after I taught KL class. One of my students in the class sent me an email with the link to the paper. Okay, this was in the archive. I think it was also published in some conference. The thing is short number 5. The title is short number 5. And if you look at the abstract, this is actually interesting. We present solutions to a century-old problem known as short number 5. What is the largest number n such that blah blah? This is actually the description that I gave. We obtain the solution n equals 160. By encoding the problem into propositional logic and applying massively parallel satisfactory solving techniques on the resulting formulas, we constructed a valid and validated proof, blah blah, and multi-CPU ear computations. Okay, and the proof is 2 petabyte in sizes, and blah blah. So you might think this is very weird because this is such another big number, right? How can be 5 and 160? Okay, this is big number. I mean, you can actually compute serial number up to 4 pretty quickly, but serial number 5 is not possible. Now, theoretically, it is known that serial number 6 is at least 536, and serial number 7 is 1680. Now, if you can find serial number 6, you can publish a paper, and you can be famous. However, the authors of this paper that shows serial number 5 equals 160 says that's probably impossible with the current computational resource. So it is not undecidable problem. It is decidable problem, but it requires massive computation power. Okay? So, however, we will actually formalize this problem, which is actually the whole program that you see. And you can actually check the answers. So I checked until, okay, actually I checked with my computer, serial number 5 is at least 130. That was just 1 minute. Okay, that's the last thing that I checked. Right. So if you want to, I don't know, be famous, maybe you can try serial number 6. Okay? All right, so I will tell you how to do that in the answer set programming next class. Okay?